So we'll start off with our usual public service announcements. Just so you know, for those of you that are going to resubmit your lab reports, you got 2 weeks to do it. Please do not let it sneak up on you. These last 4 weeks of the semester are going to go by really, really stinking fast. So don't get yourself in trouble. Okay, today we're going to talk about control systems. And most of it is going to be about PID loops. So we've talked about power switching. I went over all that power MOSFET stuff. I told you all about high side switching and low side switching and how to turn current on and off. And then we talked about a whole bunch of different sensor technologies at a really, really high level. Okay, but now we got to start putting all this stuff together to actually do something. The example I've got for you today is this thing right here. And one of the classic examples of PID control is you heat up a block. And you try to hold a block at a constant temperature. Okay, that's a little boring. I decided to go the other way. I hooked up a Peltier cooler. So what I'm going to do, I'm going to chill the block. If you don't know what a Peltier cooler is, it is basically a solid state heat pump. I put current, I put power in, and it forces heat transfer in the wrong direction. So it's going to suck heat out of the warm side, and it's going to put it in the colder, other way around. It's going to suck heat out, and it's going to move heat into the hot side. Okay? So we'll start off really simple with this. Okay. I've got some software loaded up in this Arduino, which is very simple thermostatic control. The same thing that we have on the wall over there, where basically if you are above a set point and you want to get down, you turn the cooler on. When it crosses the set point, you turn it off. So let's look at what happens when we actually run that. I've got a modified version of my Crosby machine controller. All right, so here we are. We're at 21C in the room. I will turn on the power. And now I'm pushing about 4 amps-ish into the Peltier cooler. Get rid of my Coke can. The rebel in me said, you know, I should really have a beer can and make it a constant temperature beer chiller. But I knew somebody would get me in trouble for that, so you know, choose your battles. Okay, so our temperature is going down, down, down. Great. My set point is at 10C. And you can see the amperage on the power supply is now off. Well, it was off for a second. And now we start doing this porpoising thing, going back and forth. You know, just like the temperature in a room. It overshoots a little bit, it undershoots, and you keep going back and forth because everything is not a uniform temperature when you're doing your switching. For some things, this is just fine. If you're not worried about variation more than, you know, whatever, probably about 1 degree, 2 degrees, and you don't worry about the little variations, that might be totally fine. Okay, but with PID, what we can do is we can bring bring that temperature down, and we can actually park right at the set point with much, much lower oscillations. So we'll get rid of this. I'm going to shut this down. And let's shoot a PID program into that controller. So that's what we just saw. We're never maintaining constant temperature. We're close, but it's not constant. So now, let's start with proportional control, okay? And, I could do a whole bunch of Laplace transforms and cool stuff and, all of that. Your eyes will glaze over and everybody will fall asleep. We're going to try something a little different. And I think this analogy is going to make PID a whole lot more digestible. Instead of Laplace transforms and all of that, we're going to drive both. And what I want to do is I want to come over here and I want to be right at this mooring buoy. And I'm out on the Penobscot, and the river current is going in this direction. Okay, so what I'm going to do is I'm going to come over here on my boat, and I'm going to make my throttle setting proportional to the error, which is the distance between me and my mooring buoy. So I've got a big distance, and I'm not where I want to be. So I jam forward a whole lot of throttle, and I'm going really fast. And that's great, but I'm getting closer. And I'm going to make my throttle setting proportional to the error in distance. So I keep pulling the throttle back. And I keep pulling the throttle back. And eventually I don't have enough throttle on, and all I can do is match the river current. And I'm reaching out for my buoy, and I never get there. And that is exactly what happens in a PID loop. If you use just proportional and you try to get to set point, you never, ever get there. Okay? Because other stuff is bleeding off that energy. Just like the river current is pushing me backward in my boat. So let's see if I can demonstrate that. I've got PID programmed into this Arduino now. And what I'm going to do, I am going to set my integral factor to 0. And that's essentially going to turn off integral, and I'm going to turn off derivative. And then we'll leave just proportional. That's cold. Might have to give it a second to let this come up to temperature. Let's see, we'll let it come up to about 18. Okay. So we're coming up power on my Arduino so the program restarts. Oh, shush. And plug the power back in. Start my display. So I'm going down, down, down. And it's doing pretty much what you would expect. So my power that's being applied is proportional to the error with the set point. So the closer I get to set point, the less and less power this thing's applying. And you can see that right in the amperage. The voltage is give or take constant, but that amps is going to keep going down, down, down. As you can see, we're starting to flatten out. We're not really dropping a whole lot anymore. It still wants to get to 10C, but we might die of old age before we get there. Actually, we're not getting there. Okay. So there you go. Proportional. It just doesn't get you to set point. So let's add in some integral. And let's go back to our boat analogy. And I think I'll turn this, set my KP a little higher so it's more reactive. Turn that off so I have access to the common port. And we'll run this one. Okay, so back to our boating analogy. So I'm going to do the same thing. I'm going to set my throttle setting proportional to my error of where I want to be. So I'm still going to come along and I'm going to pull the throttle back, I'm going to pull the throttle back, and I'm going to pull the throttle back. And that's going to be going on. But I'm also going to do something else. I'm going to get antsy. So I'm going to add some time integral. So I'm going to say, okay, I'm moving along. And I'm not getting there fast enough. So, a minute's gone by. I'm going to nudge the power forward. Another minute's gone by. I nudge the throttle forward some more. Another minute. Bump the throttle forward some more. So now we got a whole bunch of throttle put on. More throttle. More throttle. Okay, all the throttle that I was giving for proportional has now died off because my error is really small. Okay, when I got all that time integral throttle on. So I've got that engine cranked right up to get to my mooring. And if I've been traveling long enough and I've been antsy enough and I got a whole bunch of throttle on, I go, oh my God, I went past my destination. Now my error is negative. And I go, whoop, take some throttle off, take some throttle off, take some throttle off, take some throttle off. And if I'm too heavy-handed, I go back, and I'm out in front of my mooring buoy. And now I gotta go, oh, stop. All right, my error is positive, add some more throttle. Add some more throttle. And eventually, yes, in fact, I can grab onto my mooring buoy, and I stay at set point. If I'm light on the throttles, if I've got a low KI value, then I can just inch up nice and slow. KP dies off. My time integral is bringing the throttle up, and I settle right at set point. Okay. That's what you get when you're critically damaged. So let's see that in this analogy, in the hardware. Okay. So now I've got a KP of 25. So I'm going to put on a bunch of power in the beginning when the error is large. And then I'm going to keep bumping it up by 0.05 every time I go through my control loop. And let's see what this does. So again, I'm going to pull the Arduino, reset the program. Already you can see something different going on. Well, you can't, but you will. So now we've got proportional, we've got integral. What you guys missed, because I was too slow, was the amperage was up at 4.5 amps when it started off. And it's still dying down, okay, because that integral hasn't had enough time to keep accumulating to bring the power back up. Still got a 10-degree set point that we're trying to hit. We're just about there. You have a little bit of noise in my readings. That's pretty darn close. And if I let it go long enough, it will in fact be right at 10. It will nail 10. Okay, let's do it again. Take the power off and let the block warm up a little bit. Let's get a little more heavy-handed with bumping that throttle forward and bringing up a bunch of throttle so that we rush headlong into our set point. Intend to overshoot. ring like all day long. Unplug that. I want you to see the beginning this time. So we're starting off at like 3.5 amps. Okay. When I was getting ready for the class, 0.05 was ringing pretty good. The difference was I was starting from about 20C. You know, I wasn't feeling rushed to keep you guys engaged. If I had 10 minutes to make you sit there bored out of your minds, then we'd have much more time for that I value to build up, and we'd be hitting set point with way more throttle on. Okay. Not as dynamic as I would have liked, but you can see that it is in fact crashing below set point right there, it's below set point there, it's below set point. It doesn't have to be below set point long before the thing just puts on a whole bunch of power. So we're oscillating about set point because I've got too much I. So you want to be very careful with I. So KP, that's your initial rate of descent. That's your initial throttle. I, you got to be careful. If you put on too much built-in throttle as you're going to set point, you're going to overshoot. You're going to ring. Okay, D. Derivative. So when I got P and I showed you that I've got this situation where I'm driving my boat, and if I got too much I on, I'm bringing that throttle up over time because I'm getting bored, which means my error can go to 0, and I can hit the set point with way too much speed. That's where D comes in. D acts like a damping. So if I'm approaching my set point too fast, that's where you can put derivative on to cut that throttle back. Okay, so you can actually use like a negative coefficient. So as my rate of approach gets faster and faster, well, it's constant. Probably want to do some math in there. But if my rate of approach is too fast, then D allows you to pull the throttle back so that you don't overshoot and ring. It doesn't really work for this example, folks, only because this is not a highly dynamic system. If I had something like a brush motor with an encoder, whereas rotating really quickly, absolutely, D becomes critical. In long-time constant control systems, you don't need derivative. As I showed you up there, as long as you're not too heavy with your I, you're all good. You'll hit set point, you'll stay right there, everything's good. Okay, it's only in highly dynamic stuff that you actually need D. I tried a couple different integral values. So you can see if I have a very low integral value, it comes and it parks right at set point. Again, this is. I think it's been happening all day. So if I've got a nice low Ki value, I come park right at set point. I was able to bump it up to 0.025, and I got a little bit of ringing when I approached the 10-degree set point. But when I went to Ki of 0.05, I got a whole bunch of ringing going on. So the more, all right, knock it off. Technology. And then I messed around with KP a little bit. So as you can see, KP will set that initial descent rate. You've got a big KP, big slope, less KP, less slope. But it doesn't affect anything at the end because your I value is going to dominate out here. So KP just gets you moving faster. Okay, so this is going to be another short lecture. That's pretty much all I got. The only other thing I will do is I'll show you the code that I use and how simple it is. Save electricity. So you would think that writing the code for all that mess would be pretty hard. I'd be intimidated by that at first glance. But what did I do? So first thing I did in my code up here, I multi-sampled my analog in. And then I derived my temperature. And all I said is the error is equal to the temperature I read at C minus the set point. That's the same as that comparator step over there. And then I said my P component is my Kp coefficient times my error. For I said I equals I plus my Ki coefficient times my error. So by adding I equals I plus the error times the constant, that's doing the time integral thing for me. So it didn't have to be anything hard. And then I did the derivative. So I said, what is the current time? And I got the time since the last pass through the loop. And I divided it by the error. So the change in error, actually. So D is equal to Kd times the rate of error. I summed it all up and I said my power setting is equal to P plus I plus D. And then I just did some stuff down here. Because the Arduino, its analog output can only be 0 to 255, I said, okay, if it's asking for a negative, set things to 0. You can't put in a negative analog right. And I also said if it's greater than 255, set it at 255. So just keep it within the limits of what the Arduino can read. And I did analog right. And that's all that a PID loop is. That's a full-on PID. I posted this in the class notes, guys, if you want to use it for anything. I know it's weight leg and capstone, but if you want a PID controller, there it is. All right, that's all I got. Any questions?